Let's begin with some basic definitions for endothermic and exothermic reactions. Let's start by defining enthalpy. Enthalpy can loosely be defined as the heat content of a system. It is a measure of the energy inside a system. Generally, if a system has lost enthalpy, it has undergone an exothermic reaction, while if a system has gained enthalpy, then it has undergone an endothermic reaction. Enthalpy is usually represented by delta H. Next, there's exothermic reaction. It can generally be described as a reaction that releases heat. The energy that is released from the reaction is greater than the energy that is required to initiate it. To generalize it in the form of chemical reaction, exothermic reactions are written as follows: reactions to products plus energy. This, however, does not mean that no energy is required on the reaction side. It just means that the change in energy is positive when comparing products to reactants. For example, in the combustion of isopropyl alcohol, the energy that is required to initiate the reaction was supplied by the stick lighter. The energy was small in comparison to the energy that was released as isopropyl alcohol and oxygen gas reacted to form carbon dioxide and water vapor. This positive difference makes it an exothermic reaction. The delta H of this reaction is negative, as the heat given off by the reaction is lost to the surroundings. In contrast to an exothermic reaction, an endothermic reaction absorbs heat. An example could be the melting of ice cubes. To generalize it in the form of a chemical reaction, endothermic reactions are written as follows: reactants plus energy to products. When a substance changes from a solid to a liquid, which is melting, or a liquid to a gas, which is vaporization, an increase in temperature occurs, which requires energy. The surrounding environment often provides this energy by losing heat. This is why you feel cooler when you sweat. As your sweat vaporizes, heat is lost from your body and given to the water to change it from a liquid to a gas. Alright, now I keep saying systems versus surroundings. In chemistry, the system is defined as the container in which the chemical reaction is taking place. Conversely, the surroundings are everything else that interacts with the system. An example of a system could be the wood in a fireplace, and the homes would be defined as the surroundings. Now, as the wood burns, heat is lost to the surroundings and dissipates throughout the house, therefore warming the entire surroundings. This is an illustration of a system giving off heat to its surroundings, such as a fireplace. Okay, now stick with me. I know it's a long process here. Entropy. It's defined as a representation of the amount of possible configurations of a system on a molecular level. Now, the larger number of possible configurations, the larger the entropy. Now, another way to look at entropy is to talk about the randomness, chaos, and disorder of a system. Solids, for example, have low entropy, while gases have high entropy. This makes sense because atoms in a solid are organized into a structure, and the only movement they are doing is vibrating, while atoms in a gas are colliding with other atoms, spinning and moving in an infinite number of directions at very high speeds. To predict the position of a single atom at any given time would be impossible, due to the amount of shear disorder going on in the system. Entropy is represented in chemistry by delta S. Alright, now we got to that part. Let's start by examining the combustion of isopropyl alcohol using this equation. Delta H is equal to delta H of the products minus delta H of the reactants. So let's start off with the product side, namely carbon dioxide. Now it has 6 moles in the equation, and these 6 moles are multiplied by the negative 395.5 kilojoules per mole of each. Next, we're going to add the entropy of water. Now, water has 8 moles for this reaction. The 8 moles are going to be multiplied by its delta H of negative 241.8 kJs per mole. The next step would be to subtract the delta H of the reactants, starting with the 2 moles of isopropyl alcohol. These 2 moles are going to be multiplied by delta H of negative 318.2 kilojoules per mole. Now next would be the 9 moles of oxygen. Now, due to the fact that oxygen is in its natural state, there is no delta H. We calculate it as 0. 9 moles times 0 is, of course, 0. We will now use a calculator just like this one to add and subtract these numbers. The total change in the enthalpy for the products is negative 4,307 kilojoules. Note how the moles of isopropyl cancel out with the kilojoules per mole of the delta H. The end result will be in kilojoules. We will now subtract the change in enthalpy for the reactants. Negative 4,307 minus negative 636.4 would equal negative 3,671 kilojoules. Now, because you have a negative delta H, the combustion of isopropyl alcohol would be considered an exothermic process.
Okay, now that we've seen what the math looks like for combustion of isopropyl alcohol, let's actually perform the experiment. So, we use this 2-liter container as a contained system. I'm using 91% isopropyl alcohol. Just going to add some to the bottle. The cap back on. I'm going to add some energy here. Just a little bit of heat.
This is the combustion of isopropyl alcohol done in lower light conditions to better visualize the reaction. This reaction is the production of ice packs using cornstarch and salt and green dye for color. Now, to perform this reaction, we're going to have to create a system in which there's a lot of heat to be absorbed. In order to do this, we're going to add some water to a pot on the stove. We're going to turn on the heat just for a little while and gain some energy. Now in this measuring cup, we're going to put some salt, a lot of salt. We're going to take this measuring cup with the salt and add it to our system, which has now accumulated quite a bit of heat, as you can see by the steam. Now we're going to mix that up a little bit, just to kind of distribute the ions of the salt evenly throughout the water. On top of that, we're going to add the cornstarch. Now, the cornstarch is going to immediately start emulsifying in the pan. As you can see, it gets harder and harder to stir. Now, while we're doing that, we're going to add some green dye. Mix the green dye very evenly and thoroughly, and you end up with these nice ice packs, which are a brilliant green. This is a great example of an endothermic reaction.